Welcome to this walkthrough of LeetCode problem number 544, Output Contest Matches. In this problem, we'll explore how to simulate a tournament pairing process, reducing the number of teams each round until a winner emerges. By the end, you'll have a solid understanding of the algorithm and its implementation. Let's dive in. In this problem, we are tasked with simulating a tournament where teams compete in successive rounds until a single winner is determined. The number of teams, represented by the integer n, is always an even number and is also guaranteed to be a power of 2. Teams are labeled from 1 to n, and in each round, adjacent teams face off in matches. The winner of each match advances to the next round, while the loser is eliminated. A match is represented in the format winner, loser, and the process continues until only one team remains. Our goal is to generate a hierarchical string representation of the entire tournament, showing how matches are formed in each round and how winners proceed. The input to our function is the integer n, and the output is the organized string representation of the competition matches, which follows this hierarchical format. Let's look at an example where n is 4. With 4 teams, the first round consists of 2 matches, Team 1 versus Team 4, and Team 2 versus Team 3. The winners of these matches advance to the next round. In the second round, the winners from the first round face off in the final match. The hierarchical format groups these matches by rounds, so the output for this example is 1 4, 2 3. This output string preserves the structure of the tournament, showing which teams competed in each round and how the winners progressed. Now, consider a larger example where n is 8. In the first round, there are 4 matches, Team 1 faces Team 8, Team 4 faces Team 5, Team 2 faces Team 7, and Team 3 faces Team 6. Each match produces a winner, and these winners advance to the second round. In the second round, the winners from the first round are paired in new matches. For example, the winners of Match 1 and Match 2 compete, and the winners of Match 3 and Match 4 compete. This process continues in a hierarchical fashion until the final round, where the last 2 winners face off to determine the overall champion. In the second round of the example with n equal to 8, the matches are as follows: the winner of 1 8 competes against the winner of 4 5, and the winner of 2 7 competes against the winner of 3 6. Finally, in the last round, the winners of these 2 second-round matches face each other to determine the overall champion. The hierarchical output string for this entire tournament is 1 8, 4 5, 2 7, 3 6. This format preserves the structure of the competition, clearly showing how the winners progress through each round. The constraints ensure that n is always a power of 2, which guarantees that every team has an opponent in each round, and the hierarchical format allows us to represent the progression of matches in an organized and complete way. When tackling LeetCode problem number 544, the goal is to simulate a tournament where teams are paired in each round, and the number of teams is halved until only one winner remains. The challenge is to construct a string representation of these matchups at every stage of the tournament. To solve this, several approaches were considered. The first is the brute force approach, which directly simulates each round. Here, we start with an array of team labels, like 1, 2, n. In each round, we pair adjacent teams, format their matchup as Team 1 and Team 2, and store the results in a new list. Once all pairs are processed, the current list is replaced with the new one, and the process repeats until only one team remains. While this approach is simple and intuitive, it has a time complexity of (n*log n) due to the iterative halving of teams, and the repeated string concatenation can bring the complexity close to (n²). This makes the brute force method inefficient for larger numbers of teams. To address this inefficiency, the optimized recursive approach was considered. This method uses a divide-and-conquer strategy to construct matchups from the outermost layer inward, avoiding iterative simulations. A recursive function pairs teams by dividing the range in 2, recursively pairing each half, and wrapping these pairs in parentheses. This approach reduces redundant operations and streamlines the process significantly. The optimized recursive approach has a time complexity of (n*log n). This is because the recursion depth is proportional to log n, as the number of teams is halved at each level, and each level processes (n) elements. By minimizing the use of intermediate lists and reducing redundant string operations, this method achieves better performance compared to brute force. Another alternative considered was the iterative optimized approach, which mimics the recursive strategy but uses a single list that is updated in place during each round. Here, a while loop is used to repeatedly pair teams, overriding the first half of the list with the formatted matchups and reducing the effective size of the list after each iteration. The iterative approach also has a time complexity of O(n*log n) and is memory efficient, as it avoids creating new lists. However, it can be less intuitive to implement compared to recursion. Ultimately, the optimized recursive approach was chosen for its clarity and efficiency. The divide-and-conquer strategy aligns well with the hierarchical nature of the problem, and the insight that the tournament structure inherently follows a recursive pattern simplifies the implementation. This eliminates unnecessary intermediate states, making the solution both elegant and performant. The recursive approach was chosen because it provides an excellent balance of efficiency and clarity. By avoiding the overhead of managing multiple intermediate lists, as seen in the brute force method, recursive pairing streamlines the entire process. Additionally, the divide-and-conquer structure aligns naturally with the hierarchical nature of the tournament, making the code easier to understand and debug. While recursion can introduce stack overhead, the depth is limited to log n, which is manageable given the problem's constraints of n being at most 10,000. Comparing the approaches, the brute force method, while simple, is less efficient due to repeated string concatenations and list manipulations. On the other hand, the iterative and recursive approaches are both efficient, but recursion stands out as more intuitive for the problem's structure. In conclusion, the recursive approach strikes the ideal balance between clarity and performance, making it the optimal solution for constructing the contest matchups in this problem. This problem is about simulating a single elimination tournament where teams compete in pairs, and the winners move on to the next round until only one team remains. The goal is to construct a string representation of all the matchups for each round. To begin, we initialize a list of strings where each team is represented by its number, such as 1, 2, and so on, up to n. We then use a while loop to repeatedly simulate tournament rounds until we are left with a single team. During each round, we pair the first team with the last team, the second team with the second-to-last team, and so on. For example, if there are 8 teams, we pair Team 1 with Team 8, Team 2 with Team 7, and so forth. Each pair is represented as a string in the format A, B, making it easy to combine and track matchups as the tournament progresses. Once the matchups for the current round are created, the list of teams is replaced with this new list of matchups. This updated list then becomes the input for the next round of pairings. The process is repeated in this way, reducing the number of teams by half each round, until there is only one element left in the list. This final element represents the complete structure of the tournament, showing all matchups from each round in a nested format. The result is a single string that captures the entire elimination process. This approach ensures that the strongest and weakest teams are paired appropriately in each round, adhering to the tournament structure. Additionally, by representing matchups as strings, we can easily build and maintain the nested structure required by the problem. The recursive nature of the tournament, where each round depends on the results of the previous one, is a key aspect of the solution. The algorithm relies on two main data structures: a list to store the current teams or matchups in each round, and strings to represent individual matchups like 1, 16. The list is updated after each round to reflect the advancing teams, while strings are used to build the nested structure of the tournament. From a complexity perspective, the algorithm is efficient. The time complexity is O(n*log n), since we process all teams in each round and the number of rounds is logarithmic with respect to the total number of teams. The space complexity is O(n), because we only need to store the list of matchups for the current round. The algorithm handles edge cases gracefully. For the smallest input, where n equals 2, the output is simply 1, 2. Since n is guaranteed to be a power of 2, we don't need to handle invalid inputs. Moreover, the efficient pairing and updating process allows the algorithm to handle large inputs without issue. Let's walk through an example where n equals 8. Initially, the teams are represented as the list 1, 2, 3, 4, 5, 6, 7, 8. In the first round, we pair the first and last teams, the second and second to last, and so on. This results in the matchups 1, 8, 2, 7, 3, 6, and 4, 5, forming the new list 1, 8, 2, 7, 3, 6, 4, 5. In the second round, we pair these matchups 1 8, 4 5, and 2 7, 3 6, resulting in the list 1 8, 4 5, 2 7, 3 6. In the third and final round, we pair the two remaining matchups, producing the final string 1 8, 4 5, 2 7, 3 6. This string represents the entire tournament structure, showing all matchups from start to finish. The algorithm efficiently constructs this nested representation step by step, demonstrating its effectiveness for any valid input size. This solution simulates the single elimination tournament described in the problem by repeatedly pairing teams until only one matchup remains. The find contest match function begins by initializing a list of team numbers represented as strings. For example, if n equals 8, the list will start as 1, 2, 3, 4, 5, 6, 7, 8. The algorithm then enters a loop that continues until there is only one matchup left. In each iteration of the loop, the function creates a new round of matches by pairing the first and last teams, the second and second to last teams, and so on. These pairs are formatted as strings in the form A, B, where A is the team from the beginning of the list and B is the team from the end of the list. For example, in the first round with n equals 8, the pairs would be 1 8, 2 7, 3 6, 4 5. This process is repeated for the next round, reducing the number of matches in half each time. For instance, the second round would produce 1 8, 4 5, 2 7, 3 6. Finally, the loop terminates when only one match remains in the matches list. This single string represents the full sequence of matchups for the tournament, and it is returned as the result. The algorithm efficiently handles the pairing process in n log n time, making it suitable for input sizes up to the problem's constraints. This is the Java implementation of LeetCode problem number 544, output contest matches. The solution mirrors the Python approach by initializing the teams as strings and iteratively pairing them until a single match remains. Key differences include the use of Java's ArrayList for collections and explicit type declarations. The logic is identical, ensuring correctness and alignment with the problem's requirements. In this problem, we are tasked with pairing teams in a contest until only one match remains. The teams are numbered consecutively from 1 to n, and in each round, the first team is paired with the last, the second with the second to last, and so on. The results of these pairings are stored as strings in the format Team 1, Team 2. This pairing process continues across multiple rounds, repeatedly having the number of matches, until we arrive at one final match string. For example, if we start with 4 teams, the initial setup would be 1, 2, 3, 4. In the first round, the pairings will be 1 with 4 and 2 with 3, resulting in the matches 1, 4, 2, 3. In the next round, these matches are paired together to form a single final match, which is represented as 1, 4, 2, 3. This is the output for n equals 4, showing how the process progressively narrows down to a single result. Now, let's consider a larger example with n equals 8 teams. Initially, the teams are 1, 2, 3, 4, 5, 6, 7, 8. In the first round, we follow the same pairing strategy, matching 1 with 8, 2 with 7, 3 with 6, and 4 with 5. This gives us the matches 1 8, 2 7, 3 6, 4 5. In the second round, we pair the results of the first round. 1 8 is paired with 4 5, and 2 7 is paired with 3 6. This produces the new matches 1 8, 4 5, 2 7, 3 6. In the third and final round, these two matches are paired together, resulting in the single final match 1 8, 4 5, 2 7, 3 6. The process demonstrates how the pairing mechanism operates consistently across rounds, having the number of matches each time until only one match remains. For a smaller example with n equals 2, the process is much simpler. The teams start as 1, 2, and since there are only 2 teams, the first round directly pairs 1 with 2, producing the final match 1 2. This highlights the base case of the problem, where the pairing is immediate. From these examples, we can make a few key observations. First, the pairing strategy always ensures symmetry, with the first team matched to the last, the second to last, and so on. Second, the process naturally follows a recursive structure, where each round reduces the number of matches by half, leading to a logarithmic reduction in size. Finally, the use of strings to represent the matches allows for straightforward concatenation of results as we progress through the rounds. The Python code provided demonstrates how this process can be implemented programmatically. The code begins by initializing the teams as a list of strings representing the team numbers. It then enters a loop that continues until only one match remains. Within each iteration, it pairs the first and last teams, the second and second to last, and so on, storing these results as strings in a new list called next_round. Once all pairs have been processed, the matches list is updated to next_round, effectively reducing the list size by half. This process repeats until there is only one match left in the matches list. At the end, the final match is returned as a string. This approach efficiently implements the pairing strategy and ensures the contest matches are generated correctly for any given n. To begin analyzing the time complexity of this solution, we start with the initialization step. Here, the list matches is created with n strings, where each string represents a team, such as 1, 2, and so on, up to n. This requires iterating through the range of numbers from 1 to n, which takes n time. Now, let's consider the pairing process. During the tournament, we repeatedly pair teams until only one match remains. The number of rounds required is determined by the fact that the number of teams is halved at each stage, resulting in log 2, n, rounds for n teams. Within each round, we pair the first team with the last, the second with the second to last, and so on. This pairing requires n operations initially, as it depends on the number of teams in that round. Since the number of teams decreases by half in each subsequent round, the total work across all rounds can be expressed as a geometric series, n operations in the first round, n/2 in the second, n/4 in the third, and so on, until the final round involves just 2 teams. This breakdown gives us a clear view of how the work is distributed over the rounds. Now, if we calculate the sum of this geometric series, n plus n/2 plus n/4 plus 1, it converges to 2n, which simplifies to n. Combining this with the log 2, n, rounds, the overall time complexity becomes n log n. Shifting our focus to space complexity, the input list matches initially requires n space to store the strings representing the teams. Additionally, during the pairing process, a new list next_round is created in each round to store the paired matches. The size of next_round starts at n/2 for the first round, reduces to n/4 for the next, and continues having until only one match remains. The maximum memory required for any single next_round list is n/2, which is simply n, when we consider the asymptotic growth. This effectively captures the memory usage for intermediate storage during the tournament. Next, we consider the memory used during string construction. Each pair of teams is concatenated into a string in the format Team 1, Team 2. As the tournament progresses, these strings grow longer, with the final match string including all teams in a nested structure. However, this growth occurs within the same lists, meaning no additional memory is allocated beyond the existing matches and next_round lists. Therefore, it doesn't increase the overall space complexity. Summing up, the total space complexity is determined by the size of the matches list and the next_round lists, both of which scale linearly with the number of teams, leading to an overall space complexity of n. For comparison, a brute force approach that generates all possible pairings in each round would result in an exponential number of possibilities, making it computationally infeasible for large n. Our optimized solution, by contrast, pairs teams iteratively, reducing the number of elements by half each round. This ensures the time complexity is n log n, and the space complexity is n, making it far more efficient. Finally, this problem's structure guarantees that the best, average, and worst-case scenarios all share the same time and space complexities. The operations performed are deterministic, so the time complexity remains n log n, and the space complexity stays n in all cases. To mathematically prove the time complexity, we note that the geometric series representing total operations, n plus n/2 plus n/4 plus 1, converges to 2n, which simplifies to n. Multiplying this by the log 2, n, rounds of the tournament, we arrive at the final time complexity of n log n. For space, the memory usage is dominated by the storage of the matches and next_round lists, which together require n memory. These analyses highlight the efficiency of the optimized solution, ensuring it performs consistently well even for large input sizes. When solving this problem, there are a few common mistakes to watch out for. First, incorrect string concatenation can cause issues. For example, forgetting to wrap team pairs in parentheses, like A, B, leads to malformed output. The fix is simple: always ensure that each pair is properly enclosed in parentheses and that concatenation is correct in every round. Next, not handling the base case properly is another frequent error. If your implementation doesn't account for when only one team is left, it could result in infinite loops or index errors. To avoid this, check explicitly if the number of teams has been reduced to 1, and terminate the process at the right time. Another mistake is improper index calculation when pairing teams. For example, pairing team I with the wrong opposite team disrupts the results. To fix this, pair team I with n(i1), where n is the current number of teams. Finally, inefficient string operations, like using plus equals in a loop, can degrade performance for large inputs. It's better to use a list to build strings and join them at the end for efficiency. These points, when addressed, can greatly improve the accuracy and performance of your solution. Now, let's focus on additional tips and insights. One common variation is assuming non-power of two inputs, which complicates the implementation unnecessarily. Since the problem guarantees the number of teams is a power of 2, you can simplify your solution by trusting these constraints. From an interview perspective, pattern recognition is a key takeaway. This problem tests your ability to identify recursive or iterative structures in pairing, and highlighting this during an interview demonstrates your problem-solving skill. Edge case handling is another critical area. For example, your solution should handle the smallest input, such as 2 teams, and still produce a properly formatted output. Efficient string manipulation is also worth mentioning. Using techniques like list-based string construction instead of repeated concatenation not only optimizes performance but may also impress the interviewer. Lastly, be ready to discuss trade-offs between recursive and iterative approaches. Explaining your choice and its advantages in terms of readability and performance can make a strong impression. Let's explore related problems and alternative approaches. Similar problems include LeetCode 22, generate parentheses, which also requires proper placement of parentheses, and LeetCode 60, permutation sequence, which involves generating specific sequences through iterative logic. LeetCode 241, different ways to add parentheses, emphasizes recursive placement, and LeetCode 895, maximum frequency stack, focuses on iterative processes with constraints. As for alternative approaches, one option is the recursive method. Here, you recursively pair teams in each round until only one team remains. This approach is clean and intuitive, as it breaks the problem into smaller subproblems naturally. However, recursion can lead to stack overflow if the input size becomes too large. On the other hand, the iterative approach uses a loop to simulate each round, reducing the number of teams by half in every iteration. It's more memory efficient since it avoids the recursion stack overhead, but implementing it correctly can be tricky, especially when handling string manipulations. Each method has its strengths and weaknesses, and the choice often depends on the specific requirements of the problem. Another variation you might consider is the hybrid approach. This combines the best of both worlds by using recursion for logic clarity while relying on iterative methods for efficient string handling. For instance, the recursive structure can determine the pairing logic, while iterative string manipulation ensures performance remains optimal. The main advantage of this approach is that it strikes a balance between clarity and efficiency. However, it does come with its own challenges, as combining both methods can make the implementation slightly more complex compared to sticking with a purely recursive or iterative solution. By understanding these trade-offs, you can choose the method that best suits your needs while keeping both readability and performance in mind. Great job making it to the end. To summarize, we tackled the output contest matches problem by simulating a tournament structure. Along the way, we highlighted key algorithms and optimization techniques. Keep practicing similar problems to strengthen your skills. Thanks for watching, and happy coding! That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!